I want to do a couple more examples really quickly. So, and for these examples, I'm not going to write out like every single rule that I've been using, just because it's very time consuming and we already went through that in the last video. But you can continue to do that just to reinforce those rules. Okay, so let's differentiate this function. When I first look at it, it doesn't really look like anything that I can attack with the quick rules that we just learned. However, the trick is that you can rewrite this function. Okay, and I can rewrite this by writing 3 plus x raised to the negative 2 power squared. I can write this as the product of two binomials. And then I can use FOIL to expand this. So I end up with 9. Okay, the product of my outers, I have 3x to the negative 2. And then I have plus 3x to the negative 2 again. And I have x to the negative 4th power. And this simplifies as 9 plus 6 x raised to the negative 2 power plus x to the negative 4th power. And I haven't even taken the derivative yet. All I've done is rewrite my function. But now I can use the power rule. I can use the sum rule. I can use the power rule. I can use the constant multiple rule. So y prime is given by, okay, the derivative of 9 is just 0. The derivative of 6x to the negative 2 is negative 12x to the negative 3 using the power rule and the constant multiple rule. And the derivative of x raised to the negative 4th power is negative 4x to the negative 5. I'm going to just clean this up a little bit. My y prime is negative 12 over x cubed plus, or sorry, minus 4 over x to the 5th. Okay, and then that is my final derivative. And the key of this example, the point I'm trying to make is, try to rewrite your function so you can, this often makes it much easier to take the derivative. And sometimes it's the only way to make it possible. So rewrite. A second question I want to ask is for this same function, find the equation of the tangent line to, and I'm also going to refer to this as f of x. You'll see why later. And if you want, you can write 1x to the negative 2 if you prefer. You can write it as 1 over x squared, squared at x equal 1. So this is a standard question, and I just want to do an example just to refresh your memory from the last chapter. So remember, to find the equation of the tangent line, we need first to find the slope of the tangent line, and conveniently that is given by the derivative. So f prime evaluated at 1 is going to be equal to negative 12 over 1 cubed minus 4 over 1 to the 5th. So this is negative 16. So that is the slope of my tangent line. We also need a point that the tangent line passes through. So fortunately, if we know that x is equal to 1, we could just plug that right into our function. So we have, let's see, 3 plus 1 over 1 squared, which is 4 squared, which is 16. And once I know this information, I can use point slope form for the line. And I have y minus, okay, so this point then is the point, I have my x value 1 and my y value 16. So this would be y minus 16 is equal to negative 16 was my slope, and x minus 1. So that's this point. And I'm just going to clean this up a little bit. So this gives me y minus 16 is equal to negative 16x plus 16, which implies my tangent line is y equal negative 16x plus 32. So here's a second example. And again, I'm asked to differentiate a function, but none of the sort of basic rules we have so far seem to apply. So I'm going to try once again to rewrite this function into something simpler. So g of t can be rewritten as, I can rewrite this fraction as the sum of two fractions. I'm also going to rewrite this with rational exponents. So this can be rewritten as t to the 3/2 power. And I'm going to write this also, in this case, with rational exponents. And you'll see why in a second. So I can see that these cancel nicely. And I end up with 7. Okay, and then I have my plus. And in this case, t to the 3/2 divided by t to the 1/2 is equal to t to the 3/2 minus 1/2. And this is just 7 plus 3t. Okay, so I haven't calculated the derivative yet. So most of the work went into rewriting the function, but you can see that this function is much simpler in appearance than this function. And taking the derivative, I just use the constant rule here and constant multiple and power rule here. So the derivative is given by 0 plus 3. So our final answer is that the derivative is just equal to 3. In this example, we are asked to find for which values of x does our function have a horizontal tangent line. So we know that horizontal lines have slope 0. Okay, and we know that tangent lines, the slope of a tangent line is given by the derivative. So what we really have to do is we need to figure out where this function, where the derivative of this function is 0. That means that the slope of the tangent line for that x value is 0, and we have a horizontal tangent line. So let's do that. So I'm going to take the derivative. Okay, and this derivative is equal to 0, so the slope is equal to 0. Slope of the tangent line is equal to 0. This will occur when 2x is equal to 4 or when x is equal to 2. Okay, so the reason I pick such a simple function is because most of you can graph it, and we can actually sort of visualize the tangent line. So this function, 1, 2, 3, 4, this is a parabola, and the parabola opens upward. It has x-intercepts of, you could see, 0 and 4, and it opens upward. So the axis of symmetry will be right through x equal 2. And you can see that the vertex is at 2, negative 8. So let me just do a quick sketch. Of the parabola. And then we can note that when x is equal to 2, just as we expected, you could see that it has a horizontal tangent line. And this tangent line has equation y equal negative 4. So that is our horizontal tangent line. Lastly, I wanted to do one example that involves a function with absolute value. Okay, and the first thing I want to do is I want to just graph this function so you can see what it looks like. Now, in order to do that, I'm first going to graph the inside function and ignore the absolute value. So if I graph 1 minus x squared, I can see that this is just a parabola that opens downward and has x-intercepts 1 and -1 and y-intercept 1. So this parabola looks like this. Okay, and another way to graph this function is to, if you recall function transformations, so if I start off with the most basic parabola, y equal x squared, then I can, if I multiply it by -1, it gets flipped across the x-axis. And if I add 1 to it, it gets shifted up by 1 unit. And this guy is just equal to 1 minus x squared. So that's another way to remember how to graph parabolas, you know, or you can also just graph the intercepts, the, you know, vertex, etc. Okay, so how do I use this graph to find the graph of the absolute value of 1 minus x squared? Well, the basic idea is that the graph will be the same wherever this graph lies above the x-axis. And whenever this graph lies below the x-axis, we're going to be reflecting, that portion of the graph gets reflected across the x-axis. So that's going to happen over here also. Okay. And that's the basic idea. And the reason behind it is just that when this quantity is positive, that corresponds to this guy lying, the graph lying above the x-axis. Okay, and so we leave it alone. The absolute value doesn't change anything. But when this quantity is negative, and that corresponds to the portions of the graph that lie below the x-axis, then the absolute value flips the sign, right? We take the opposite sign. Okay, so let's just draw what that looks like. So as I said, from -1 to 1, the graph is going to look exactly the same. Oops. I'm going to draw that a little better for you. And then over here, the graph is going to be reflected. And same thing happens over here. Okay, so that is what the graph of this function looks like. And so now let's talk about what is f prime of x. Well, the first thing I'm going to point out just from looking at the graph that you can see is that these are sharp points, and derivatives do not exist when you have these sharp sudden changes like corners, cusps, or sharp points. So we can immediately see that f of x is not differentiable at x equal -1, 1. Okay, but it's smooth, nice and smooth and differentiable everywhere else. But we've got some problem points at 1, x equal 1 and x equal -1. Let's try now to find f prime of x. So first I want to rewrite f of x as a piecewise function, so in a different form to make it easier for us to see what's going on. So remember that if this quantity is positive, then the absolute value is just equal to that quantity itself. Now that this quantity being positive corresponds to when the graph of the inside function was above the x-axis. So that occurred when x was between 1 and -1. Now, if this quantity here is negative, then the absolute value is going to give us the opposite of that quantity. So -1 minus x squared. And where does that happen that this quantity is negative? Well, that happens for the x values where the the inside function was below the x-axis and we had to flip it. Okay, so that would correspond to x being less than -1 or x being greater than 1. Okay, so using this information, we can calculate the derivative. Okay, so the derivative f prime of x, and we know it's not defined when x is -1 or 1. The function is not differentiable. You can give a more rigorous proof of that. I'm not going to go into that in this video, but I believe the textbook and the WebAssign homework does. So I'm just going to take the derivative of this guy, and we have -2x if x is between but not including -1 and 1, and the derivative will be equal to +2x. So I'm just using the basic rules like the power rule and the constant rule, and that is true if x is less than -1 or if x is greater than 1. And again, I don't include -1 or 1 in either of these because f prime is not defined there because of the sharp point.